The chemistry we all know was developed when hydrocarbons, water, and energy were all plentiful and cheap. And we had the luxury of taking the most abundant sources of rarer materials. But this just can't be sustained, meaning we've got three key challenges. Firstly, the challenge of making chemistry much more energy efficient. And nitrogen fixation is a great example of this. Most of the nitrogen in our own protein and DNA comes through plants, and these plants depend on fixed nitrogen in the soil. Unfortunately, natural fixation is nowhere near enough to feed 6 billion people, let alone the 9 billion that we're forecast to have in 2050. Biologists are really working hard to extend biological nitrogen fixation, but of course this uses photosynthetic energy and therefore reduces crop yield. Chemical fixation of nitrogen is really energy demanding, but it just seems essential if we're to keep on feeding the world. Surely with modern catalysis and increasing pressure on energy, there are some really significant improvements to be made here. Secondly, biological carbon comes mostly as carbohydrate and as polymers with complex structures, rather than hydrocarbons that we're used to. So what a great challenge to invent a whole new chemistry to provide the properties we need in materials and chemical products from this completely new source. And finally, we need to find ways to recycle critical elements and molecules, for example, rare earths and phosphate, rather than returning them to the environment in a dilute form. So pushing that further, energy efficient separation may also turn out to be critical in ensuring we have enough fresh water both to drink and to grow our food. Thank you. David Lawrence.